right, good afternoon, good evening, or good morning, everybody, depending on wherever you're joining us from. So it's my pleasure to talk to you today about compact HF antennas. And by HF, we obviously mean high frequency, but this is some sort of a historical name because that refers to antennas that are working or frequency range that covers, the 3 to 30 megahertz frequency range. So these days, it's a pretty low frequency, but in the early days of wireless, that was a pretty high frequency, and so the name is sort of a historical name. So what I'm going to be talking about, in this lecture, I'm going to talk a little bit about radio wave propagation at the HF band, talk about noise at the HF band, some fundamental limitations on electrically small antennas, talk about receive and transmit antennas at the HF band. And all of these are before we talk about any antenna. And as we'll see in the lecture, this is a very interesting frequency range, and the performance of antennas is really not separate from the performance of the communication channels or the nearby environment that the antenna is located in. So, it's important to have some understanding of what these things are before we actually get to talk about the antennas. And then, the antenna part of this, I've kept it very, very simple. So we'll talk about primarily small antennas, electrically small antennas at the HF band. So, talking about some basic radiating elements, the problems of impedance matching, and so on and so forth. And so this lecture is an introductory lecture. So, if you are somebody who has taken an undergraduate course in electromagnetics or electromagnetic wave propagation, and maybe have seen some basic antennas, you should be good. So this would be relevant for you. If you're somebody that's an advanced graduate student or somebody who's already experienced in HF, a lot of things that I'm talking about here you already know, so that probably wouldn't be too much of interest to you. So I think the target audience for this lecture are, senior undergraduate student, maybe first year graduate students, or any sort of practicing engineer that's not already familiar with the operation at HF band. So with these clarifications, let's get into the materials I want to talk about. So what we're looking at here, in this picture, is sort of a snapshot of planet Earth and atmosphere around the planet Earth. So on the right-hand side of this picture here, let's see, on the right-hand side here, what we're looking at is, so this is Earth, and then, we're going up in the atmosphere, and, there are different layers in the atmosphere, starting from troposphere, stratosphere, mesosphere, thermosphere, and so on and so forth. And then this is a picture of the sun. And what happens is that, there's a lot of radiation coming from the sun towards the planet Earth. Obviously, we see, sun in the visible spectrum, but, there's a whole lot of non-visible radiation that's coming from sun and other stars, in the infrared region, in the ultraviolet, and then going up to X-rays. And a lot of these radiation that's coming from the sun is ionizing radiation. So ionizing radiation means that the photons are energetic enough that can ionize, atoms. And when you think about our atmosphere, we have oxygen, we have different types of, molecules, oxygen and nitrogen, and, other molecules in the atmosphere. And these molecules, can get ionized. And so what happens is that in a region over in the atmosphere, approximately, let's say from 50 kilometers to about 600, 700 kilometers or so, there's a region of the atmosphere that we call ionosphere. So this is the region where, we have a lot of ionized molecules, and generally what we do is we divide this region into different layers. We call it, there's multiple layers, like D layers, E layer, F layer. Sometimes, during the day, this F layer is divided into F1 and F2 layer, and so on and so forth. And these are not exactly very well defined layers, but, these are the different layers of the ionosphere that have, different concentrations of free electrons in the ionosphere. And so what we can do is, we can sort of consider a very simple Drude type model for the dielectric property of plasma. And so these layers that I talked about here, when you're ionizing these molecules, you have, these free, these ionized charges that can move, in the atmosphere. And so this sort of forms a plasma, and we can characterize this plasma reasonably accurately with some sort of a Drude type dielectric constant model for the plasma. So the formula that I have here, is the equation for the dielectric constant of plasma, a lossy plasma based on the Drude model. And so in this formula, what we're looking at here, we have a couple of terms. Epsilon naught here is the free space or the dielectric constant of vacuum, 8.85 times 10 to the minus 12. This omega p is our plasma frequency, and nu is the collision frequency. And these are two parameters that are important in plasmas. And omega is the frequency of the wave that may be passing through this medium. So for such a medium, we can define an effective dielectric constant. And then the plasma frequency, there's a closed form formula that you can come up with for the plasma frequency, which relates the number of electrons in per unit volume and the charge and mass of these electrons to the plasma frequency. And so if you go ahead and plot this function, the real and imaginary parts of this function, for let's say, a collision frequency that's about a tenth of the plasma frequency, you get a dielectric constant like this. And the key point here is that if you're working below the plasma frequency, you'll see that the dielectric constant of this medium is negative. So this is quite important because this impacts how electromagnetic waves propagate, in this plasma. So now, if you look at a very simple propagation problem, in a sort of an electromagnetic plane wave propagation. Imagine that, I have a slab of a material with that dielectric constant, with sort of a plasma, a non-magnetic material, but with a plasma dielectric constant. So what happens in this environment? So imagine that I have an electromagnetic wave. This is a plane wave that's trying to propagate in the positive z direction through this slab, and you can simply go ahead and calculate the complex propagation constant of this wave here. And it's going to be something that has a real part and an imaginary part. If the dielectric constant is a complex number here, and you can go ahead and plot, the real and imaginary parts of this this propagation constant and see what happens. So here I've done it for a lossless plasma, a plasma where, in this equation, nu is equal to 0. So the dielectric constant is a real number. It's either, a negative real number or a positive real number. And so here, what you're saying is that below the cutoff or below the plasma frequency, so on the horizontal axis here, we have frequency normalized to the plasma frequency. You see that below the plasma frequency, alpha is non-zero and beta is 0. So this complex propagation constant becomes a real number, and you'll have exponential attenuation of the wave as it propagates through the medium. And above that, you have normal propagation. So this is very similar to what happens in a waveguide, for example, below the cutoff frequency, right? And then if you have an actual real plasma, which, this is generally what we have in real life, you have a dielectric constant that has both a real part and an imaginary part. And, the picture becomes a little bit more complicated, but the general trends are still the same, that below the plasma frequency, you have primarily attenuation of the wave, and above the plasma frequency, you have primarily propagation. And then the further away you're from that plasma frequency, the less the attenuation of the wave, would be. So this is a very simple example. Now, in reality, the ionosphere that's surrounding the planet Earth here, it does act like a plasma, but it's also, a magnetically biased plasma. So its dielectric constant, ends up being slightly more complicated than what I showed. It's going to be a gyrotropic medium, and wave propagation in that environment, has much more interesting properties. But for the purposes of our discussion today, we actually don't get into that. So now let's see what happens. Let's see what the plasma frequency of the ionosphere is around. There are a number of different factors that impact the density of electrons that we'll have, in the different layers of the ionosphere. So obviously, the radiation that we're getting from the sun has a significant impact on this, and therefore this is going to be different, during the day or during the night. At night, there's no direct sunlight, and so these ionizing radiations that would cause the generation of the plasma would not be as strong, or in some cases, would disappear. And during the day, especially in midday when the sun is really directly blasting, things would be different. So these are some interesting numbers about the typical electron density that we have in the different regions of the ionosphere, let's say at midday and at midnight. And you can convert these typical electron densities using the formula that we showed previously in the previous slides to plasma frequencies. And so you see that, for example, in the D layer of the atmosphere, in the ionosphere, the plasma frequencies are generally in the 100 kilohertz to a megahertz range or so. And then as we go higher in altitude, then the density of electrons increases, and then our plasma frequencies go up. So for example, for the E layer, we're looking at the megahertz to about a couple of megahertz, and then for the F layer, we're looking at a few megahertz to sometimes 10, 12 megahertz or so during the day. And then at night, then because the density of because there's no solar radiation which keeps ionizing, the atmosphere here, then some of these, then the densities actually will go down, and these plasma frequencies will go down. So there's a lot of things that will impact that. So obviously the time of day is one factor, but the solar activity, some years, depending on the solar cycle, some years, we have more solar activity, and some years we have less. The season, if you're in the summer or in the winter, and your location on the planet Earth, all of these will impact what the plasma frequency of these different layers of the ionosphere would be. But the key interesting thing is that if you look at these frequencies here, these are all pretty much in the HF frequency band, right? In the 3 to 30 megahertz frequency range or so. And so this tells us that in that frequency range, electromagnetic wave propagation should have really interesting properties. So you can go ahead and these plasma frequencies of the different layers of the ionosphere, or the electron densities of these different layers. These are things that are of interest in a lot of different applications, not only for HF communications. There's a lot of space weather predictions and things of that would also require knowledge of these, and there are a lot of different stations out there distributed, over the planet Earth, that actually measure this, and they do that by using some sort of by using what's called an ionosonde. And so, if you want to think about this very simplistically, so imagine that you have this is a very simplistic picture here, but imagine that I have an antenna here, and I sort of and this is my ionosphere here. And I'm illuminating this ionosphere with waves at different frequencies and looking at different returns, and so I get a curve, kind of like this. And so what we're looking at here in a curve like that is a frequency range from 2 megahertz to 18 megahertz in this case, and you're looking at the return of these waves from the ionosphere, and there's a lot of data here. But for example, if you look at, for example, these two curves that we have here, these show. For example, if you look at 7 megahertz, this show, that you're transmitting something that goes up and then comes back down. It's at you have a reflection at approximately about 300 kilometers or so, and then as frequency goes up, there's a frequency here that roughly around 15 megahertz or so that you're sending waves, and then your waves are not coming back down at you, right? And so from that, you can say, oh my God, this is like the plasma frequency of my F layer of the atmosphere in this case. And obviously these are these ionograms are things that change depending on the location. This particular one that I'm showing here is from Lualuale in Hawaii for December 22nd of last year here, and you can go on this website and look at graphs like this for a lot of different stations at different locations, especially if you're interested in operations at the HF band. Now, these numbers, these plasma frequencies, become very, very important, as we'll see, in a little bit in the rest of this lecture. So as I mentioned, there are a lot of these stations, throughout the world that measure the plasma frequencies at different or have these ionograms at different times of the day. And there are resources that again are freely available. For example, you can go to this website here and plot a map on the planet, a map of the planet Earth, and then plot the different the plasma frequency of different layers. And so here what we're looking at is the plasma frequency of the F2 layer of the ionosphere. The F layers of the ionosphere are particularly important for operations at a high frequency band. And so what you're looking at here is, you see some contours and some numbers here, right? And so in this case, this particular graph is again on December 22nd of last year at a time where in the Western Hemisphere, on the eastern part of the United States, we're looking at midday, and so you can see that our plasma frequencies here are pretty high. So these are around 12 megahertz in here, and then at the same time, obviously on the other side of the planet, Earth in Asia, it's in the middle of the night, and so the plasma frequencies are pretty low. So the critical frequencies of the F2 layer are changing, and all of these are obviously impacting our HF communications, as we'll see in a little bit. So having a knowledge of the atmosphere and the ionosphere around us is important. But why is that important? Well, so let's see what happens, if you're trying to communicate, with electromagnetic waves at frequencies that are close to the frequencies, the plasma frequencies of the ionosphere. So we can envision a number of different ways that we can launch an electromagnetic wave. So imagine that, for example, I have an antenna here, and I'm launching an electromagnetic wave, vertically up towards the ionosphere. So what happens here is that, depending on the frequency of this wave, if the frequency of the wave is below the plasma frequency, then, I get primarily a reflection of the wave back. So if I launch this wave directly, vertically up there, then if the frequency of the wave is below the plasma frequency of the layer, then the wave gets reflected back. Now, if I'm located here, and let's say I'm launching a wave, not necessarily vertically up, but with an angle here, right? And this angle, is what we call the launch angle or the takeoff angle. And the way that we measure that angle is we measure it from the horizontal plane. So if you're here on the planet, on the surface of the planet, this is locally your Earth is flat, so this is basically tangent drawn to the surface of the planet. And then if you're launching a ray towards that direction, then this is your launch angle or the elevation angle or the takeoff angle of your ray here. So as you are launching this wave, when the wave gets into the ionosphere, a number of interesting things happen. Number one, because this is a magnetically biased plasma, as your wave enters the ionosphere, it separates into two modes. We call these modes the ordinary and the extraordinary modes, and then they travel over different paths. And as they are traveling, they also get refracted, and so that your wave, sort of gets curved and then bends and then comes back towards the Earth. So if you are an observer, located here and are monitoring this wave, to you, it may seem that the wave that's launched actually is reflected back from the ionosphere. So oftentimes we use this term and we say, oh, our waves bounce off the ionosphere or get reflected from the ionosphere. And if you draw basically straight lines between the paths of these waves, it seems that we have a point where this wave is reflected from. And so this is something that we generally say, but in reality, your waves actually are refracted and sort of bend back down. But for the purposes of a communication system that's working here, the details of that don't really matter too much. The key point though is that your waves are, if you're working over a certain frequency range, your waves are refracted or reflected back towards the Earth. And so imagine that, I'm sitting, I have an antenna here, I'm launching a wave, the wave goes up, comes down here, maybe goes up and comes down there. And you can imagine that, the Earth and the ionosphere form some sort of a waveguide that your wave can bounce off between the Earth and the ionosphere to travel over very, very long distances. So this would be a way for us to use HF waves or electromagnetic waves in these frequencies for what we call beyond line of sight communications. So you don't need to have a direct line of sight between the transmitter and receiver, and you can communicate over very, very long distances. There are some other applications, for example, over the horizon radars that also use the same concepts here. So bouncing off of the wave between the Earth and the ionosphere to have waves that propagate significantly over significant distances and significant distances that go beyond line of sight. So this is very interesting because you really don't need a lot of infrastructure. You can just use the properties of the Earth and the ionosphere and have very, very long distance communications with very simple infrastructure here. Now, another interesting thing that happens here is that let's say that my plasma frequency for the ionosphere is 10 megahertz here. And if I launch a wave vertically towards the ionosphere and the frequency of this is below 10 megahertz, then the wave gets reflected back. But if the frequency is above 10 megahertz, then the wave passes through and just goes off into the outer space. On the other hand, if I launch my wave with an oblique angle of incidence towards the ionosphere, so let's say the angle of incidence here is theta, then the wave can still be refracted back or reflected back towards the Earth if the frequency of the wave is even larger than 10 megahertz. So this is a concept that we call, maximum usable frequency. So in other words, when you're launching a wave at an angle from the towards the ionosphere, the frequency of your wave doesn't necessarily have to be below the plasma frequency of the ionosphere. So in this example, I may be able to communicate at a frequency of 15 or 20 megahertz, which is above the plasma frequency of the ionosphere, but it's still, because I'm illuminating the ionosphere with an oblique incidence angle, then that wave can be refracted back towards the Earth, and I still can be using higher frequencies, for establishing that long range communications. And so approximately, you can sort of think about the maximum usable frequency and the plasma frequency of the ionosphere to be related with this formula, where in this formula theta is the elevation angle or the takeoff angle of your ray. Now, what are the ways that we actually can bounce off, waves off the ionosphere and have communication? So let's say, for example, this is a simple picture. Let's say we are looking at the E layer and the F layer of the ionosphere here, and I have a transmitter located here, and I have receivers at multiple different distances. And this curved line, this is my Earth here, right? And so let's say that you have an antenna here, and this antenna is launching waves. And this RX1, the first receiver, is located reasonably closely to the transmitter. And by reasonably closely, what we mean is, I don't know, maybe 100 miles, 200 miles or so, not very far from the transmitter. So what happens here is that, if you have a wave that you're launching towards the ionosphere at an angle that's not exactly vertical, but it's very close to vertical, then, that wave, and if the frequency is below the frequency of this E layer of the ionosphere, then the wave can get reflected back towards the receiver here, and you can have establish a communications, right? You can also, let's say, if the frequency of the so we know that the plasma frequency of the E layer generally is in the 3 to 4 megahertz range, and then the plasma frequency of the F layer, let's say, for example, is in the 8 to 9 megahertz range or so. So let's say here, if I have a frequency of, I don't know, 3 megahertz, then this can get reflected from the E layer. But now, if I have a frequency of, let's say 7 megahertz or so, what happens? If I have a 7 megahertz, then this wave actually, goes through the E layer, but it can be reflected off of the off of the F layer and then come back towards the Earth at the location of this second receiver here. Or if I'm launching my wave, at a steeper angle here towards the F layer, then it can be reflected from the F layer and then come back towards the first receiver. So these modes of communications, we call those near vertical incidence sky waves. So the vertical incidence or the near vertical incidence is because of the fact that we are launching these, towards the ionosphere almost with vertical angle of incidence, not exactly vertical, but with angles that are pretty close to vertical. Hence, the term near. And then sky waves is because your waves are launched towards the sky and then they're reflected from the different layers of the ionosphere back towards the ground. And so these are called NVIS, modes of operation. And then we can also have another mode of operation where now you're launching your waves with lower takeoff angles. So let's say, for example, this green ray here. It's pretty low takeoff angle, and we are launching it with an angle towards the E layer. And notice that now our theta is smaller, so that f of e over sine of theta now is a larger number. So in this case, the frequency of this may be, I don't know, 6 megahertz, still higher than the plasma frequency of this, but it still may be reflected by the E layer and arrive at a receiver that's located at a longer distance. And so this distance may be maybe 1,000 miles or so now, right? And so this is an example of a situation where we call these sort of modes as long range sky waves, because the separation between the transmitter and receiver are significantly larger. So you need to launch your waves with lower takeoff angles to be able to cover that distance here. Now there's between the same transmitter and receiver number 3, there are multiple paths that you can have, right? So for example, I can have a one hop. This is what we call a one-hop link, that reflects from the E layer. But I also can have, a one-hop link that now is launched with a larger takeoff angle. Now this ray is passing through the E layer and is getting reflected by the F layer and then arriving at this location. Or I can even launch a ray, with even a steeper angle and have 2 hops that, get me to that point. And so all of these are different modes that you can use for establishing a long-range skywave communications. All right, so these are things that you can model. So here, for example, I did a simulation, modeling of a link between Madison, Wisconsin, and Orlando, Florida, and this modeling was done for Thursday, December 26th of 2024 at around 1900 UTC. And so at what we're looking at here on the left-hand side, this is showing a section of the map of the United States, and these contours are showing the plasma frequency or the critical frequency of the F2 layer of the atmosphere, and so or of the ionosphere. And so notice, for example, these numbers, they're telling 12, 11, 11.2, 11.7. These are the contours that tell us the plasma frequency of the F2 layer of the ionosphere. So this is Madison, Wisconsin. This is Orlando, Florida. The distance is slightly above 1,000 miles or so, and midway between the path, somewhere here, maybe in Tennessee or so, our plasma frequency is approximately 12 megahertz or so. And so you can do a modeling, of a communication link between these 2 regions, and you can generate ionograms like this. So this is what we call an oblique sounder ionogram, and this is a simulation result. And on the horizontal axis here, we have frequency, in megahertz, and on the vertical axis, we have the elevation angle of the waves that are launched between the transmitter and the receiver. So let's say this is my TX, this is my RX location, so TX and RX, and I'm launching rays, with different elevation angles here, and they are getting reflected from the ionosphere, from different layers of the ionosphere, and they are arriving at the receiver. So what we're looking at here is, if you look at this curve here, notice, the legends here tell us hop one, hop two, hop three. So the black lines, these are one hop links here, right? So it means that, all these black lines, these are all the rays that are launched from my transmitter with a given launch angle that arrive at the receiver at different frequencies. So for example, we'll see that, if I can launch a ray at an angle of 2 degrees or so from my transmitter, uh, over this frequency range, of up to almost 18 gigahertz or so, between 2 and 4 degrees, then I can establish a link, between Madison, Wisconsin, and Orlando, Florida. So this would be 2 to 4 degrees takeoff angle, and 0 degrees is basically horizontal, right? Is your ground. And this is a reflection from the E layer of the ionosphere. And then, at starting approximately at, frequencies around 10 megahertz and then going up to 26 megahertz or so. Now, if I launch rays, with takeoff angles of about maybe anywhere from 14 to 20 degrees or so, then I can have a one hop link that takes advantage of the reflection from the F layer of the ionosphere. And then, over the same frequency range, you can have, if you look at these blue curves, these are now the uh, uh, two hop links that I have, and then you can have three hop links and so on and so forth, right? These rays, if you have an antenna, generally your antenna is not sending the energy only in one direction, it's sending the energy towards multiple directions, and then the receiver on the other end is also receiving from multiple directions. So you can have, these modes of propagation that utilize reflections from the E layer, from the F layer, maybe one hop, two hops, and so on and so forth. And we'll see the significance of these elevation angles. So, a little bit later in the lecture, we'll see the significance of these elevation angles. But one thing that I want to emphasize right now is that, actually designing HF antennas that give you these sort of elevation angles very close to Earth, is very challenging. So that's not a very easy thing to do. And we'll see a little bit of this, later on. So, by the way, again, I remind you that at any point, if you have any questions, just feel free to interrupt me, or put a question in the chat box, and Sima will be monitoring that, and we can I'll be happy to answer those questions as well. Don't necessarily need to wait until the end to ask your questions. So there is one other mode of propagation in the HF between a transmitter and a receiver as well, which is what we call a ground wave propagation. I'll talk a little bit about that. In this lecture, we don't really focus on it too much, but it's good to know a little bit about it. And so, so a ground wave propagation basically refers to waves that don't require interaction with the ionosphere here, right? No NVIS or no long range skywave type propagation. And so, for example, imagine that I have a small dipole antenna here located at the distance of h, above Earth here. And we have a receiver that's located at that location. So you can imagine that there's obviously if these antennas are in line of sight of each other, there's a direct wave between the transmitter and the receiver. There is a wave that's going to be reflected from the Earth and then arriving at the receiver. So the signal that you're receiving here is the sum of this direct wave plus the reflected wave. And if the transmitters and the receiver antennas are located very close to the ground, then you also have this mode. You have also a surface wave mode that propagates between the transmitter and the receiver, and then the surface wave has the property of actually following the curvature of the Earth. And so now imagine that I have an antenna, a transmitter antenna, a receiver antenna that are located pretty close to the surface of the Earth, and then I can launch a surface wave that follows the curvature of the Earth, and so you can have beyond line of sight propagation in these situations by taking advantage of that surface wave as well. And the surface wave has interesting properties. You can couple to that when you're using vertically polarized antennas. So, for example, your antenna here, needs to be a vertical monopole or a vertical dipole, and the receiver there, should be something like that as well. And these waves tend to propagate better over surfaces that have better conductivities, and then over poorer surfaces, they don't propagate as well. And so here, we're looking at a curve here where we are looking at on the vertical axis, we're looking at frequency, and on the horizontal axis, we're looking at the distance that a typical surface wave can propagate over. And so, for example, if you're at lower frequencies, around 2 to 4 megahertz or so, these waves can propagate over very long distances. In this case, 80, 90, 100 miles or so. And as higher at higher frequencies, then the propagation, is not as doesn't go as far. The best environment for the surface wave propagation is over seawater. So, for example, let's say this is the Atlantic Ocean here, and we have a lot of water here, and so you have a vertically polarized antenna there, another vertically polarized antenna there. So, because the seawater is a really good conductor at these frequencies, then that would be pretty much the best sort of environment that you can have for propagation of these surface wave modes at the HF band. So this is good to know. Again, in what I'll talk about in the rest of the lecture, probably we don't focus too much on the surface waves, but okay. So now let's also briefly talk about the issue of noise, at the HF band. And so noise is important because in any sort of a communication system, where our objective is to transmit information at a transmitter and then receive information at a receiver, this receiver has to process, the received signals in the presence of noise. So let's say this is your signal and this is your noise. And, you always need to have a given signal to noise ratio that would allow you to demodulate and retrieve the information that's contained in the signal you're transmitting there. And depending on the modulation, your signal to noise ratios, are different. Now, one important thing about operation at the HF is that HF, this frequency range, is an extremely noisy environment, and there are a number of different sources for noise that are important. By far, the most important one is the man-made noise here. So basically, what do we mean by man-made noise? We mean, the noise that's generated by all sorts of electronics and electrical instruments that humans have created that did not exist in nature. So let's say, you have your automobile, the ignition, spark plugs of your automobile, your washing machines, any sort of electrical appliance, your power lines, the engines of all sorts that use electricity, for lighting up, fuel in the internal combustion engine, high voltage transmission lines, switches, any sort of power electronic circuits, all of these are devices that are created by man that generate electrical noise, electrical emissions, and these emissions actually tend to be primarily very, very strong at frequencies in the HF band. Let's say below 30 megahertz, primarily significant below about 15 or 14 megahertz or so. And so all of that contributes to making this environment an extremely noisy environment. And in a little bit, we'll see why this is important. There's also cosmic noise, so emission by the sun and, the stars in the center of the Milky Way and all of these, these are also contribute to noise at the HF frequency band. Although these become a little bit more significant at higher frequencies than the HF, because again, that ionosphere, when it's blocking signals radiated from Earth from going into a space, it also does the same thing for signals or noise that's coming from outer space, into the space. And there's also atmospheric noise. So this is something that people don't create, but these are from natural events. So let's say you have lightnings, and thunderstorms, and these thunderstorms and lightnings, they don't have to happen in your area. So let's say I'm working in Madison, Wisconsin, and there's some some winter storms, I'm sorry, some summer thunderstorms in Florida. There seems to be one every afternoon in Florida, and there's lots and lots of lightning. The signals radiated by these propagate over very long distances, so that can create noise, over a significant area. And these generally tend to be very significant at lower frequencies. Sometimes, you actually, if you're operating in this frequency range, you hear noise that may be associated with thunderstorms that are thousands of miles away. So to get a picture of what the noise environment in the HF band is, there are some really good models, provided by ITU. ITU stands for International Telecommunications Union, and there's some documentation provided by ITU that you can go ahead and read. I've provided a link to this documentation here that have provided formulas for these different noises, ranging from man-made to galactic to atmospheric noise. So in this picture, in this slide, I'm actually showing some of the numbers that we basically generated for a given case. So in this case, for example, we assumed that we're looking at a typical environment in the city. So let's say, for example, in downtown Chicago, and we're looking at a bandwidth of 3 kilohertz. And at the time, we assumed that, the critical frequency of the F2 layer of the ionosphere is about 10 megahertz. And my PhD student, Eric Weber, he wrote a really nice MATLAB code that we can put all of these, and use the ITU models and then get the information about, what sort of noise figure we are expecting to get from these different sources. And so in this figure on the left-hand side, you're looking at a noise figure associated with these different sources, so the galactic noise here and the atmospheric noise, and the black line here is the man-made noise, and then the pink line is the total noise. And you see that in this particular example, the man-made noise really is the major contributing factor to the total noise in the system that we are seeing, right? In this particular example, the contribution of these other ones, even though non-zero, they don't seem to be as significant as the noise generated by the mankind. So that seems to be your dominant noise factor. And then the noise powers that we are looking at, are, let's say, over that bandwidth or so, we're looking at approximately, let's say, for example, if you're at a frequency of 10 megahertz, you're looking at minus 90 dBm or so of noise power over that 3 kilohertz bandwidth. And this is a significant amount of noise that's just coming from the environment. So, and this makes things a little bit challenging to work at. So there's a question here. Let's see. Are there spherical modes that can be excited? Is it reasonable to view Earth as a sphere with multi-layer electric slab or as two concepts? Oh, that's a good question. So this is about, let's see if we go back to our picture of here. So these spherical modes, I think, if we go down in frequency, I think looking at so the question for those for everybody else is that the question is that, okay, the Earth and the ionosphere, if you think about that, it forms some sort of a spherical cavity, right? So the surface of the Earth and the surface and let's say the lower layer of the ionosphere. And do we have a spherical cavity that has a spherical modes here? And I would think that when you go down to very low frequencies, so let's say the VLF frequency, where your wavelengths are, significantly larger than the wavelengths that we have at HF, then probably, we'll have, looking at this in the form of a spherical modes may be a little bit more appropriate. So in the HF, our wavelengths are approximately 100 meters at 3 megahertz to 10 meters at 30 megahertz. And then if you look at the different layers of the ionosphere here, let's say the lowest layer of the ionosphere is approximately at 50 kilometers, 50, 60 kilometers. So this is still significantly larger than the wavelengths. So even though we have technically a cavity, this is a highly overmoded cavity. So in this case, it's probably easier for us to actually think about, ray tracing and rays, sort of bouncing off of the Earth and the ionosphere to get a picture of this. So technically, it is a cavity, but again, it's a really, really highly overmoded cavity. That picture, I think, becomes a really interesting picture when we go to very low frequencies, the VLF, for example, let's say 100 kilohertz or 10 kilohertz or so, where now our wavelengths are significantly larger, and now the dimensions, the separation between the Earth and the D layer of the ionosphere becomes kind of like comparable to the wavelength, and then it becomes a little bit easier to think about this as a cavity with traditional spherical modes. Um, so, like I said, at any point, if you have any questions, just interrupt me. You don't need to, like, I mean, if you put a question in chat, that's fine, but I may not see that immediately. So feel free to interrupt me.
Yeah, if the questions are put in chat, please send it to me as well. I think this question wasn't sent to me, so I
Okay.
can monitor it if it comes to me.
Okay. All right. That's
Yeah,
okay.
yeah.
But anyway, this is so again, don't be shy. I tend to just go and talk, and so just interrupt me.
Okay.
All right.
I have a question on
Sure.
polarization. Like on the
Yes.
slide with the ground propagation, you mentioned that vertical polarization is
Yes.
preferred over like horizontal. Do
Yes.
you have a comment on this, the NVIS type? Is there a the skywave, is there a polarization preference?
So for the sky, that's a very good question. And for the sky waves, it's you can so let's say for example, we're looking at the NVIS. Um, Technically, um, so I have my Earth here, and then this is, let's say, my ionosphere. So, because I have to launch a wave, towards that direction, and we tend to use, like for practical reasons, when we talk about antennas, let's say we tend to use like antennas in the form of, basic dipoles or basic loops, quite a lot at these frequencies because the antennas, tend to be pretty large. So one common type of antenna that is used quite a bit, is basically a horizontal dipole antenna, right? So this is a dipole that's horizontal with respect to Earth, and so that gives you horizontal polarization, but not necessarily because your wave is uh, would not be reflected, if you have vertical polarization, but because if you have, let's say, if you want to have a vertically polarized wave that's generated by, let's say, a dipole antenna towards uh, uh, the vertical towards the ionosphere, then that becomes a little bit challenging because my dipole antennas have nulls. But for these long range sky waves, you can have communications with both vertical and horizontal. So a lot of times, it comes down to more practical reasons, of the types of antennas that you can actually use, which sort of a polarization you'll use. The other thing that's important is that, and we didn't really talk about this too much, but the other thing is that, let's say for a long range sky wave, I have, a transmitter, here and a receiver located there. And then the wave is launched, goes into the ionosphere. So your waves, would be sort of, as the wave enters the ionosphere, it splits into two modes, the ordinary and extraordinary modes that propagate over different paths. And then when they come out, you'll get some sort of polarization rotation, right? You get a Faraday shift of that. So let's say you're transmitting your wave with a given polarization. On the other end, you may not exactly get the same polarization. Like, the best thing that you can do if you really want to be capturing all the data or have a very reliable communication link, would be to use maybe a vector sensing type antenna. But the propagation of the wave in the ionosphere is a very interesting concept. It's quite a bit more complicated than what I mentioned, especially because of these different modes that exist. So these would be different circularly polarized modes with different phase velocities and go through different paths. And then when they come out and they combine, they cause a polarization rotation of your wave. But in general, you have you can establish these communications for both vertical and horizontal. For ground wave, this one is an exception, especially for the surface wave mode of the ground wave communication, where horizontally polarized, but well, you have to have vertical polarization to be able to couple to that surface wave mode.
Thank you.
You are welcome. All right. So let's see, where were we? Oh, I'm going in the wrong direction. So we are, okay, so we were here, we were talking about noise. So now, so what I've done here is, again, I've used Eric's quote here and plotted, the same noise power in the HF as a function of frequency for different different environments. So let's say, imagine this black line, downtown Chicago. These may be suburbs of Chicago, and then this may be, I don't know, some southern Wisconsin rural area, and then this may be some really northern Wisconsin, quite rural area. And you see that, as we go to more, as we go away from the inventions of mankind, the noise actually goes down. But, even in a quite rural area, the noise is pretty high. And so what I've also plotted here on this line, this horizontal line, this is KTB. So this is basically the absolute thermal noise that you'll have at a given temperature. So, this is KTB at, room temperature, let's say 20 degrees Celsius. And over for that bandwidth of 3 kilohertz. So the B is my bandwidth, T is my temperature, and K is the Boltzmann constant here. So for a bandwidth of 3 kilohertz, the thermal noise that you'll have in an impedance match resistor is going to be about minus 139 dBm or so. So if you're working at 10 megahertz in the middle of downtown Chicago, the noise that you're getting from your environment is around negative 90 dBm. So a significant difference between these two numbers. So what is the consequence of this? Well, the consequence is that in any sort of a receiver system, you have a given noise figure, right? So typically, when we have a receiver antenna here, we have a low noise amplifier here, and then, have, the different subsequent stages of our receiver. And, we're using, this receiver to demodulate and retrieve our information. And so we define a noise figure for this entire system as the ratio of the signal to noise ratio at the input of the system. So for example, if this is my radio, the signal to noise ratio at the input to the signal to noise ratio at the output here. So let's actually do some really simple back of the envelope calculation here and see what the consequence of having a very noisy environment at the HF is. So let's say, for example, I have a receiver with a noise figure of 8 dB, and I'm working at a frequency that there's really negligible noise from outside of my antenna terminal. And let's also say that I need a signal to noise ratio of about 6 dB at the output of my receiver to be able to demodulate the signal properly. So let's say, for example, I have whatever, a QPSK modulated signal, and I need 6 dB signal to noise ratio. And I'm just throwing things out here. If somebody listens to this and, if the signal to noise ratio for QPSK is lower or higher than that, please don't fault me on this. I'm just trying to make a very simple case here. So let's consider that 6 dB here. So what is the signal intensity that I need to have? So here in this case, you go ahead and calculate your KTB, and this ends up being around negative 139 dBm for a 3 kilohertz bandwidth. And because you have a noise figure of 8 dB and you need 6 dB of signal to noise ratio to be able to demodulate this system, you need to have a total signal to noise ratio at the input of your receiver that's about 14 dB. And that means that the power that you're receiving should be 14 dB higher than the noise power in your system, and that's around minus 125 dBm. So if you have a minus 125 dBm of received signal or received signal power, then you can successfully demodulate that data. Now let's see what happens, at 10 megahertz in the middle of downtown Chicago here. So, as we saw in the previous example, the noise power that I'm getting from the outside environment is negative 90 dBm here, right? So this is basically what I'm getting really outside. And, if I need a signal to noise ratio at the input of my receiver, that should be 14 dB higher than the total noise, then the power that I'm looking that I need to have in order to be able to do the same thing in a really noisy environment, is going to be significantly higher. In this case, it's going to be around minus 76 dBm or so. So here, this is again a very simple back of the envelope type calculation to tell us that when we are working in a regime where there is a lot of noise coming from the outside environment into our receiver, and there's some noise generated by our receiver, but the noise that's generated by our receiver is much less than the noise that's coming from the outside environment, we are externally noise limited in our systems, meaning that we are noise limited by the external environment and not necessarily by our receiver. When we work at much higher frequencies, frequently we are generally internally noise limited by our receivers and the sensitivity of our receivers. But HF, is a pretty noisy environment. So the consequence of this is that this actually makes the task of impedance matching for many receive applications at HF frequencies pretty much irrelevant in our antennas, because when we design antennas that have that have better and better impedance matching, we are letting more noise come from the external environment into our system. So there's basically a level of impedance matching for receiving antennas that we need to have, but beyond that, we're not going to get any improvement in the receiving system. For those of you who are old enough to have opened up an AM transistor radio, and if you actually do that, and open that up, you see that the antenna inside this is a teeny tiny ferrite core, with a lot of turns of a wire on it, and it's a very small antenna that's not very well impedance matched, and it works well because again we are working at frequencies in the order of 1 megahertz or so, where the environment is extremely noisy. All right, so these are some of the things that are important about the environment at HF and the noise on HF. And now we want to start talking a little bit about antennas. And this is a good
Can I
time.
ask a question before
Yeah.
we turn to them?
Yes,
So
absolutely.
the noise information that you mentioned, it can be accessed from IT. How often
Yes.
is that updated? Like, can we imagine, like, with the environmental changes and with the new technologies that are coming up,
Right.
this will
That's a
change?
good question. This is no, I don't think this is updated very frequently. I think it is updated. These recommendations are updated every once in a while. I don't remember exactly what the date of this particular document was. I think it's a couple of years old now, but uh, but but they are not updated on, let's say, on a yearly basis or anything like that. And
Mhm.
yeah, I mean things get changed. Especially like for example in power electronic circuits, the frequencies of power electronic circuits keep going up and up and up, right? So
Yeah.
things probably will get worse and worse and worse at the higher end of the end of the HF frequency band. So probably, let's say, this man-made noise, may sort of change like this, in the
Yeah.
future. But yeah, I mean, it is what it is, right? So
Hmm.
at the moment, we're just using what's out there.
Do we have information about the surface waves that you mentioned in this type of documents? Like,
Yes,
can you
well,
imagine, like, noise
there
is
is.
also different there?
Well, noise is so the surface wave. There's quite a bit of information about the surface wave. Both there's a lot of information. So here, for example, this picture, is from a reference that I borrowed this picture from. There's a chapter that talks about, like, surface wave propagation at the HF, and has really good references there. The noise wouldn't be significantly different for surface wave versus a sky wave, because all of these noise uh, numbers that I'm putting. So basically, these models that ITU provides, it's assuming that, oh, you have a vertical monopole antenna, on a really good ground, and these models are derived for that. So yeah, I mean, the environment, as the environment changes or as the technology changes, these values, these numbers can change, but also
Mhm.
like depending on the type of antenna that you have, this also can change. So what the purpose of I think the purpose of curves like this, at least for the purposes of what we do, is to have an understanding that, okay, we're dealing with a really noisy environment, and if you're doing some sort of link budget analysis, You have reasonable estimates on how much power you need to transmit, what sort of antennas you need to do, and there's going to be a few dB ups and down variations, in your link budget analysis anyway, right? It's a little bit, uncertain.
Okay, thank you.
You're welcome. Are there any other questions before we actually proceed to the antenna part of this lecture? Okay. So again, at any point, if you have any questions, just feel free to interrupt me. All right. So now let's actually proceed to the antenna part of this lecture. And first, I want to talk a little bit about fundamental limitations on electrically small antennas. So what is an electrically small antenna? An electrically small antenna is an antenna that has physical dimensions which are significantly smaller than the wavelength of the electromagnetic wave it transmits or receives. So, for example, if you have an antenna at 3 megahertz, where the wavelength is 100 meters, and if your antenna is like 5 meters, 5 meters is significantly less than 100 meters, right? So that would be an electrically small antenna. So the reason that I want to talk a little bit about this here is because this is a really important thing at HF frequencies, because our wavelength of electromagnetic waves is so large that, we are generally, in many cases, we're dealing with antennas that are very small. So this is a field that has, there's a lot of studies, done, in this field. There's a famous Chu limit that basically says that if we have an antenna, an omnidirectional antenna, but doesn't specify what the type of this antenna is, that fits in a sphere with a radius of a. So in this picture, so imagine that, this is my antenna and it fits in a sphere with a radius of a. He came up with a formula that puts an upper bound limit on the quality factor, a lower bound limit on the quality factor of this antenna, and an upper bound limit on the bandwidth of the antenna. And so the formula is given here. Here K is the wave number, 2 pi over lambda, and A is the radius of the smallest sphere that can completely contain your antenna. And this is the beauty of this. This is that it really doesn't matter what type of antenna you're dealing with, as long as it's an omnidirectional antenna, whatever type of antenna it is, this limit applies to. So with that information, you can go ahead and calculate a limit on the bandwidth efficiency product of your antenna. So for example, if we consider a bandwidth of the antenna to be defined as the frequency range over we have a impedance match with a VSWR of 2 to 1, then we have an upper bound on the bandwidth efficiency product of this antenna that's given by this equation 1 over square root of 2 times Q, where Q is obtained from here. So this limit becomes even more severe. Studies have shown that in order for us to be able to approach that limit, we need to have antennas that would use the entire volume within the sphere efficiently. So these antennas tend to be spherical shaped antennas. And so if you have, let's say, an antenna that's a planar antenna or a cylindrical antenna or a dipole antenna, then the situation would be even more severe for these antennas. So here, I've actually done in this table, I've done some calculation for an antenna with a maximum linear dimension of 2 meters. So basically, in this case, the radius of the sphere would be 1 meters and at a frequency of 10 megahertz. And I'm assuming that, I have an efficiency of 100% in my system. So the impedance matching network, everything is 100% efficient, which is not realistic, but it gives us an idea. And then we're trying to figure out how much bandwidth we can get from such antennas. And in this table, we're seeing that if the antenna has a spherical shape, the bandwidth that we can expect to get is about 43 kilohertz. And then if you have, let's say, a cylindrical antenna, the best bandwidth that we can get is about 30 kilohertz. And if it's a planar antenna, 12 kilohertz. And if it's a simple, humble dipole antenna, you're looking at a bandwidth of about 3.4 kilohertz. That's like the upper bound on the bandwidth that you can get from a system like that. So we are seeing that the bandwidths are really, really small. On top of that, let's say that we have now, this dipole antenna, right? This 2-meter dipole antenna. Now, 2 meters is 6 feet, right? It's almost as tall as I'm. It's a little taller than I am, right? So if you have a 2-meter antenna, which is physically, not very small, you can put it in your pocket, right? This antenna is extremely small electrically compared to the wavelength of electromagnetic waves at 10 megahertz, which is 30 meters. So it's a pretty small antenna. And the input impedance of this antenna is going to be an input impedance that has a very small real part and a very large imaginary reactive part. So this is a highly reactive input impedance here. Now, in most systems that we're dealing with, we impedance match our antennas, right? We typically deal with antennas that are impedance matched to 50 ohms. And so I have to go ahead and impedance match this antenna with that input impedance to 50 ohms in order to be able to transmit any power out of that. So the picture is actually kind of like this. So what happens here is that I have a load with a really high VSWR, which is my antenna, and I want to impedance match it to a VSWR of 1 to 50 ohms. And if you go ahead and solve this problem, and I did this in this example, and I designed impedance matching networks for this with COTS component, and COTS here stands for commercial off-the-shelf components, inductors and capacitors. So let's see what happens. So let's say that my dipole antenna, the 2-meter dipole antenna, is made out of a perfect electric conductor. There is no ohmic loss in that dipole itself. And I go ahead and design an impedance matching network, an LC impedance matching network with realistic inductors and capacitors. So these inductors and capacitors have loss associated with them, and we quantify the loss with a quality factor of the inductor and a quality factor of the capacitor. So here I'm assuming, for example, that I have inductors with a quality factor of 100 and capacitors with quality factors of 1,000. And these are very good quality factor numbers. And I impedance match this antenna to 50 ohms. And let's see what happens. In this picture, we are seeing that I don't have any reflected power, so my impedance matching is really good. I have about 96% of my power lost to the losses of this inductor and capacitors. So that's about 14 dB of loss just in my matching network. And let's say if in this case, let's say if my radiation efficiency of the antenna itself is 97%, so very very close to a really ideal antenna, then I only radiate 3% of the almost 4% of the power that I'm putting into this network. So most of my power gets lost in my impedance matching network. Now, an inductor with a quality factor of 100 is a really good inductor. Typically, for large inductors, we can get quality factors that are much lower. So if you go ahead and do the same exercise with an inductor that has a lower quality factor, you see that the problem, would be even worse here. So now I have something in the order of 21 dB of loss, in my components, and so collectively, when I look at my realized gain, so the realized gain of this antenna is, let's say if I'm putting 1 watt of power into this, and there is a little bit of power that's getting reflected, some power lost, and then I look at the power that's radiated from my antenna to the power that's incident, to the antenna, which is this 1 watt here. I get very low gain values. So I get gain numbers that are in the order of minus 20 dB or minus 12 dB, and these are very, very low numbers. And a significant part of this is coming because of the losses that I have in my impedance matching network. This is actually one of the reasons why HF antennas, typical HF antennas, are very, very have very, very low gain, especially electrically small antennas on the lower end of the HF band at 3 megahertz or so. So this is a concept that is well known. It's referred to as matching network loss magnification, and this happens anytime you are trying to impedance match a highly reactive load, let's say an electrically small antenna, to 50 ohms. There's a significant difference between the VSWR of your antenna and the VSWR that you're trying to achieve, impedance matching to 1 here. You'll have the small losses that you may have in your impedance matching networks would be magnified to cause a significant overall loss in your impedance matching network. The reason for this is because when we have highly reactive inductive loads, you'll have very large circulating currents and very large voltages and currents in the elements of your impedance matching network. So if you have a little bit of a resistance associated with your inductor, the Ri square loss associated with that resistor, or the V square over R loss associated with your capacitor, would be very large, and that results in significant losses. And so there's a formula that you can use for calculating the effective loss of your network. The moral of the story is that the smaller the antenna gets, the more power you lose in your impedance matching network when you use realistic impedance matching networks that have losses with them. And this picture also shows, so in this slide, I go back and very quickly revisit what we talked about a little bit earlier. I mentioned that HF is a very noisy environment, and if you're dealing with a receive-only situation, if you're not trying to transmit any sort of power through your antenna, then you may not need to really worry too much about impedance matching for a receive application. So here is some calculation that we did a while back, and we sort of looked at the effect of impedance matching in on the signal to noise ratio, or the G over T noise of our antenna system, as a function of better impedance matching. So here, basically, what you're looking at, imagine that the vertical axis is the signal to noise ratio that we are receiving from our antenna, and as we go from left to right, so we have an antenna here, a matching network, and we are designing a better impedance matching network. And my signal to noise ratio improves, but it starts to plateau here at different frequencies. So this is at 3 megahertz. At 15 megahertz, this thing goes up a little bit longer, but then at some point it starts to plateau. And so we'll see that we don't really need perfectly impedance matched antennas for receive applications at HF. So we need antennas that have good enough impedance matching, but beyond a certain point, then the impedance matching of your antenna becomes so good that now you're letting a lot more noise come from the outside environment to your receiver system, that that it really doesn't matter anymore, right? So there is that trade-off point here. So this is for a receiver antenna. For a transmitter antenna at HF, you do have to impedance match, because you're trying to transmit power, and your power amplifiers cannot be presented with a significant reflected power from your antenna. All right. So these are some, there are some important, basically, notes that we talked about, for these HF antennas. And now let's actually go ahead and see some examples of electrically small antennas at HF. Before I go ahead and do that, are there any questions so far? Okay, so we'll start with the simplest type of electrically small antenna. Anybody who has taken any course that discussed an antenna, the first type of antenna that you have discussed is basically an electrically small Hertzian dipole antenna, right? So basically, a dipole antenna here with a length that goes to 0, and the way we analyze this dipole antenna is, we assume that we have a uniform current distribution on the antenna. So let's say if the antenna length is L, going from negative L over 2 to positive L over 2 over the z-axis, we assume that we have a uniform current distribution, and this current, by the way, is I e to the j omega t here. And then we go ahead and calculate the fields radiated by this antenna, and find out that, this is, by the way, one of those antennas for which we have closed form solution for the fields radiated by the antenna everywhere, right? So you get these expressions, and then we see that in the far field, we have electric and magnetic fields radiated by this antenna that are given by these expressions. So these are obtained, these you can find in any textbook. This is the number one antenna that we analyze in any sort of antenna discussion. The second antenna that we analyze is basically the same antenna here, but now with a triangular current distribution. So here basically, if this is the end of my antenna, rather than assuming that the current is uniform, then we'll assume that, oh, the current, actually has this triangular distribution because, the current on the ends of the dipole should go to zero. You can't really have, a non-zero current at an open end, otherwise you'll have charge accumulation and that, we're violating some laws of the laws of physics there. But, both of these antennas are actually good representatives of a number of small dipoles that we'll see. So for these antennas, we can go ahead and calculate a radiation resistance, the total power that's radiated by the antenna and the radiation resistance. And these radiation resistance values have closed form formula. So for example, for the dipole that has a uniform current distribution, the equation for the radiation resistance, 80 pi square L over lambda to the power of 2. And then if you have a triangular current distribution, then the radiation resistance is 20 pi square L over lambda to the power of 2. It's basically 1/4 of that. Now, these numbers, keep in mind that for electrically small antennas, L over lambda is significantly smaller than 1. So for example, if I have a 2-meter dipole at 10 megahertz, L over lambda is 2 over 30 or 1 over 15 to the power of 2. So you have to multiply this by that number, and you'll end up having a pretty small actual radiation resistance. And that's why the real part of the input impedance of these antennas that we're dealing with is tends to be pretty small. Now, another thing for these antennas that we calculate is the directivity, right? The directivity or the directional gain of our electrically small antennas. So for a Hertzian dipole antenna, the directivity we can calculate, it's about 1.5 or 1.75 dBi. And if we assume that our antenna is 100% efficient, is impedance matched to 50 ohms with a lossless impedance matching network. All of these are invalid assumptions, by the way. But let's say for the time being, if we do that, then our gain would be around 1.75 dBi. This is basically the best gain that you can expect to get from a Hertzian dipole antenna. As we'll see, our gain actually ends up being much less than that, but that's like the upper bound for this Hertzian dipole antenna. So why is this Hertzian dipole antenna an important antenna to analyze at the HF applications? The reason is because, at HF, in the frequency range from 3 to 30 megahertz, our wavelength ranges from about 100 meters to 10 meters. And so imagine that you have a 3-meter dipole antenna. This is almost around 10 feet long, which is a pretty large antenna physically. But this pretty physically large antenna is going to be extremely small electrically speaking. So at 3 megahertz, it's only 3/100ths of a wavelength. And at 10 megahertz, it's only 1/10 of a wavelength. So over a good chunk of the HF frequency range, this antenna is pretty small electrically speaking. And if you go ahead and calculate the input impedance of this antenna, and I've done that, and I'm presenting the results in this table on the bottom of the slide. This is obtained from method of moment. You'll see that at 3 megahertz, your input impedance, the real part, is very small, less than half an ohms. The imaginary part is very large, highly capacitive reactive impedance. And then as frequency goes up, this real part goes up, the imaginary part, goes down. So the quality factor of this antenna as frequency goes up, improves. But let's say if you're working in frequencies below 10 megahertz or so with an antenna that's this small, then this is a pretty good example of an electrically small antenna. So such an electrically small antenna, that sine theta radiation pattern that we showed, it has a classic donut shape 3-dimensional pattern. So it looks like something like that, where if this is your dipole, along the axis of the dipoles, we have these nulls. So in this case, our dipole is located vertically here. And then, if you take one cut of this radiation pattern in this plane, this is going to be an omnidirectional radiation pattern. So it's just going to be radiating equally well everywhere. And if you take a cut of this, donut shape radiation pattern that includes your dipole, then you get a radiation pattern that looks like a figure 8 shape, with nulls along the axis of the dipole. This is sort of the classic radiation pattern of a dipole antenna. We'll see electrically small loops actually have a similar radiation pattern as well. So now I can take this Hertzian dipole antenna and I can apply the image theory to this. And so let's see what happens if I have a perfect electric conductor there. And if this Hertzian dipole antenna is located either vertically or horizontally with respect to that perfect electric conductor, then I can use the image theory, remove that perfect electric conductor, and now I'll get two. Let's say if the antenna is vertically oriented, I get two vertical monopoles and that are in the same direction. And if the antenna is horizontally oriented, then I get two horizontal monopoles that are oppositely directed, right? So this is the classic image theory. And so you can use this to convert your Hertzian dipole antenna to a Hertzian monopole antenna. So I can basically put half of this dipole on a perfect electric conductor ground plane. And so this becomes my monopole, and feed this monopole antenna with a voltage source connected between the terminal and the ground plane. And from the image theory, this becomes equivalent to my Hertzian dipole antenna. And so because in the process of doing that, I'm reducing the volume over which the antenna radiates, I'm essentially reducing the power radiated by this antenna by a factor of 2. When I go from a dipole to a monopole, my radiation resistance would be reduced by a factor of 2, but my directivity actually increases by a factor of 2 as well. So your input resistance goes down by a factor of 2, your directivity goes up by a factor of 2. So for an ideal monopole antenna on a perfect electric conductor ground plane, then the directivity that you can expect to have is about 4.7 dBi or so. Now, again, this is an ideal case. We don't live in an ideal case. And, if especially if you look at this radiation pattern, this is very interesting. Pay attention to this because we are going to see how this changes in real world in a couple of minutes. So here I have my monopole antenna. So let's say this is my monopole antenna right there. And this picture, this ideal picture of a perfect electric conductor ground plane, shows that this monopole antenna radiates very nicely, at these angles, at these elevation angles that are kind of like zero elevation angles here, right? Towards horizon. Now, there are a couple of issues here. Number one is that we never have an infinite perfect electric conductor ground plane, right? So whenever you actually go ahead and build something, assuming something is infinite makes our analysis easier, but, things are never infinite in extent. And so what we have to do is, we have to build things that are of finite dimensions. And so for the same monopole antenna, if I go ahead and take that monopole antenna and put it on an actual ground plane, this is a PEC ground plane, with a finite diameter for my ground plane, then see what happens. So in this case, the radius of the ground plane on the right-hand figure is half a wavelength. And notice that now this antenna doesn't have, this sort of, radiation that is only in the upper hemisphere, right? There is some radiation that goes below the ground plane, and this is because of the fact that my ground plane is finite, right? The larger I make this ground plane, the closer the shape of the radiation pattern gets to this ideal case, but I always have finite dimensions to deal with. And especially when we are dealing with HF at 10 megahertz, again, your wavelength, keep in mind that it's 30 meters. So, the diameter of this thing, is about 30 meters. 30 meters is not a small distance here. Now, if you go ahead and, increase the diameter to 2 lambda, then you see that now this starts to become a little bit more direction, the radiation in the lower hemisphere, reduces. And this thing obviously, gets closer to the ideal situation as time goes on and as you make this larger and larger. But, we are always constrained by physical size. The second thing is that even this picture is a very unrealistic picture at HF frequency. So we never have, a monopole antenna like this on a ground plane with a 30-meter diameter that's floating in a space, right? Where is this? Is this in a universe without anything next to it? No, this is going to be close to some object. And, at the minimum, it's going to be, let's say, in most situations, it's actually going to be close to Earth, right? The surface of the planet Earth. And so what is the impact of the actual real Earth on the performance of an antenna like this? And this is also something we can model. We can model these things very efficiently. So what I've done here is now I've taken that same monopole antenna that I had on a ground plane, which is a PEC ground plane. This circular object is a PEC ground plane. The radius of this PEC ground plane is half a wavelength. The diameter is about 1 wavelength or so. And then this entire thing is placed on real Earth. So this is real Earth here. And what does real Earth mean? It means that, it's basically dirt, right? Depending on where you are and what the composition of Earth is, you have a given dielectric constant and you have a given conductivity. And so in this particular case, I'm assuming that this Earth has a dielectric constant of 20 and a conductivity of 0.03 Siemens per meter. So this is what we call good Earth. So good Earth in the context of HF applications, right? So the conductivity is high enough that this is actually not too bad, right? The best sort of quote unquote Earth we can have at HF frequencies is seawater, where the dielectric constant is around 80 and the conductivity is around 4 to 5 Siemens per meter, and this becomes as close to a perfect electric conductor as we can get at HF frequencies from the actual planet Earth here. But if you are, let's say, I don't know, somewhere in rural Wisconsin where the Earth is really wet and there's quite a bit of good moisture, you may find Earth with these properties. So now let's see what happens to my radiation pattern of my antenna here. And now notice that the three-dimensional radiation pattern of this antenna is here. This is obtained from simulations in FICO. Some of you may be familiar with FICO. It's a pretty good software. I myself have started using it recently, and I find it particularly useful for some of these HF antenna simulations. So notice what happens here, right? So I had this ideal monopole antenna. This is what we teach in our antenna classes, right? As what the radiation pattern of a monopole antenna is. And this is when you get, or what you get in real life at HF frequencies, when you have an antenna, a monopole antenna placed on a really good ground plane, but with finite dimension under that ground plane, then the rest of that, is surrounded by real Earth. So your monopole antenna, this is a cut in the elevation plane pattern. So your monopole antenna is now located here. So obviously there's no radiation along the axis of the monopole. But notice what happens here. There is also no radiation along the elevation angle of 0 degrees here. So along basically this Earth, like along the horizon, you have no radiation here. So what happens here is that the direction of maximum radiation of your antenna here is now it goes up, from horizon, to an elevation angle that in this particular case is about 26 degrees. So this is what we call the takeoff angle, right? So your takeoff angle, well, yeah, let's call it the takeoff angle for this particular example. So this is the direction of maximum radiation has now gone up to 26 degrees. Now I go back here and notice that in an ideal monopole with a really good Earth, the takeoff angle is 0 degrees. So this is elevation. And notice that, in these figures, you may notice that my 0 is up and, I'm coming down. So these are the theta angles in the spherical coordinate system. For those of you who are familiar with the spherical coordinate system X, Y, Z, right? So in these simulation softwares, we are plotting this in the spherical coordinate system, but the elevation angle concept that I'm talking about in HF frequencies, that's measured from the horizon, right? From the surface of the planet Earth. So in this case, the elevation angle of 0 degrees correspond to a theta of 90 degrees. So hopefully that's not confusing. But But the key point is that now the takeoff angle of that antenna is gone up, right? And then it's not radiating things along the horizontal axis. This becomes important in using these antennas for, let's say, skywave type communications, right? Because that takeoff angle determines, which direction, or the direction of maximum radiation of your antenna determines which direction you're transmitting most of your energy towards, and, over what distances you can communicate with an antenna that has this sort of a radiation pattern. So let's see what happens, what's the effect of the size of this ground plane on the performance of the antenna. So in this case, the size of the ground plane, I mean, this perfect electric conductor ground plane that we have here, we are going to change its radius and see what happens. So if we start from lambda over 8 and then go to lambda, notice what happens here. Our takeoff angles for this antenna, as a function of the radius of the ground plane, the takeoff angles change a little bit, maybe going from 25 degrees to around 30 degrees or so. But the most important thing is that the gain of my antenna, improves here as I go from a small ground plane of let's say lambda over 16 here, and go to a larger ground plane with a radius of about 1 lambda. And notice that in these gain numbers that I'm reporting here, we are the only source of loss we are considering here is the loss of Earth here. So all the other losses of the impedance matching network, reflections, all of those are ignored. It's just the effect of the Earth. So this is basically showing what happens, even in this case where we have reasonably good Earth with dielectric constant of 20 and conductivity of 0.3 Siemens per meter, the loss of the Earth plays a significant role in reducing the gain of your antenna here. So now let's see what happens here if we have the same antenna, with a ground plane radius of 1/8 of a wavelength, placed on different types of Earth here. So here, starting from a dielectric constant of 3 and a conductivity of 10 to the minus 3, and then going up to a dielectric constant of 20 and a conductivity of 3 times 10 to the minus 2 here. And this is an example of poor Earth. And this one, 20 and 3 times 10 to the minus 2, is an example of good Earth here. And notice what happens to our radiation pattern of the antenna here. There is some changes in the takeoff angles of our antenna. Generally, as the conductivity of the Earth, improves, and as the Earth becomes better and better, then the takeoff angle comes down, gets closer to what we're expecting in the ideal case. In the ideal case of a perfect electric conductor, you're expecting the takeoff angle to be 0 degrees elevation. But now, when we have real Earth, this is not going to happen. And then the other thing that happens is that, again, considering only the loss of Earth, the effect of the real Earth on the performance of the antenna, my gain also improves here. So the conductivity and the environment that this HF antenna is located in significantly impacts the performance of your communications link and your antennas. And notice that the dB scale should be really taken seriously, because a 3 dB change in gain, that corresponds to a factor of 2 improvement or decreasing of the power. And so here, for example, from this number to that number, we are approximately 4.5, 5 dB seeing improvement in gain just because of the presence of the Earth. Now, the other thing that we need to think about is that, this picture, even the picture that I'm showing here, this one, this is more realistic, but even this one is not practical in many applications. And the reason is because, it is pretty hard to have an actual ground plane, a continuous ground plane with, let's say, a diameter of 30 meters or 15 meters or so to mount your antennas. These are physically large structures. So let's say if you want to go ahead and set up an HF antenna, and you have to treat a significant part of the ground in the vicinity of that to get anything that resembles what we are simulating. So what would be more practical is to actually implement our ground plane not necessarily with a continuous ground plane, but rather with with a bunch of radial lines here. So what you're seeing in this picture, you're seeing these wires here that are essentially radial lines that are implemented to approximate a ground plane for my monopole antenna. And so, imagine that if you increase the number of these radial lines as you increase them from the 4 that I was showing in that picture to infinity, then you get the picture that I showed previously with a continuous ground plane. So let's see what happens as I increase the number of radial lines from 4 radial lines and then go to a continuous ground plane here. And we're looking again at the radiation patterns of my antenna, and we're looking at the gain. And the only thing that's considered here, the only source of loss that's considered here is the effect of the earth. Everything else is assumed to not matter here. So as I increase the number of radial lines, notice that when I have 4 radial lines, my gain is actually pretty low here, right? I'm looking at negative 9 dB or so, and then I increase it to 8, it improves, again, negative 6, now I am at negative 3, and then, if I have 32 radial lines, I'm at negative 1 dBi, and so on and so forth, and when I get to continuous, then I have the best performance. So this is another factor, right? Practicality of the implementation of your antenna. So if it's a small antenna, you need to have a ground plane, but you can't really go and have a large ground plane for it. So the best you can do is, have a bunch of wires, lay on the ground, maybe a couple of these, 4, 8, 16, and the effect of these wires, is also significant. The more of these you have, the better the performance of your antenna would be in terms of reducing the impact of the loss of the earth, on the performance of your antenna. So, remember that when I talked about the electrically small antennas, I mentioned that we can have a uniform current distribution and you can have a triangular current distribution. So in an antenna, in a simple monopole antenna, obviously we have a triangular current distribution. Your maximum current happens at the base, at the feed point, and then the current sort of goes down in a triangular fashion, and there's zero current at the tip of the antenna. You can improve the uniformity of the current on your antenna by putting a top hat on top of your monopole. So let's say if I have a top hat like this, then this top hat acts as a capacitor, and this allows you to get a more uniform current distribution throughout the surface of your antenna. And you're seeing this picture here, in these two pictures. And so what I'm doing here is now I'm implementing that top hat also with a bunch of radial wires that you're seeing in this picture. So this picture here essentially shows a top hat loaded monopole antenna, but again, the top hat of the monopole is implemented with a bunch of radial wires because having a continuous structure is a little bit challenging. So the effect of that is as you are making the current on your antenna more uniform, notice what happens. So this is the antenna with the same height. And when I have just a single monopole antenna, notice a small real part, a very large imaginary part. And as I increase the loading of that, then the real part of my input impedance improves. The uniformity of the current helps with that. This is the difference between that 20 pi squared L over lambda to the power of 2 and an 80 pi squared L over lambda to the power of 2. And then the imaginary part of this also deteriorates. So the real part goes up, the imaginary part actually decreases, not deteriorates. So this becomes a lower Q antenna, right? So I can actually impedance match that much more conveniently. So what is the effect of that? Let's actually look at what happens when we try to impedance match these different antennas here. So here, I'm assuming that we're looking at these different monopole antennas, and we are now trying to impedance match them with this simple impedance matching network. And I also am assuming at this point that this impedance matching network is a lossless impedance matching network. And notice what happens to the VSWR 221 bandwidth of my antenna. So the black line is the monopole antenna without the top hat. And as I increase the number of top hats, and increase the number of radials, notice that, I'm able to impedance match this over a wider and wider bandwidth. So this would be, again, in the context of electrically small HF antennas, it would be a prudent thing to do because we are dealing with such inefficient and narrowband antennas. Now, the other thing is that when you actually start thinking about realistic impedance matching networks for such an antenna, and you take into account the losses in your matching network, then you'll see that the effect of the quality factor of your antenna becomes even more important. So for example, in the same 4 cases that we examined before, so this was our impedance matching network that was lossless, so a lossless matching network. And now I'm going to make that impedance matching network a lossy matching network. So those inductors and capacitors, I'm assuming that they are good inductors and capacitors, Q of 100 for inductors and Q of 1,000 for capacitors at 10 megahertz, which are really good numbers, but nonetheless have some loss associated with them. So let's see what happens to the losses that I'll have in these realistic matching networks. And so notice that, for the impedance matching network or a simple monopole antenna without top hat, I'll have something like 10, almost 11 dB of loss in my matching network. That's a lot of loss, right? So that converts the gain of your antenna to about negative 10 dBi, very low gain. And then as I increase the number of radials, and the quality factor of my antenna goes down, that problem of matching network loss magnification, that is improved. And now I lose less power, so 4 dB and almost 3 dB and 1 dB for a continuous solid top hat loss in my matching network, and then the gain of my antenna improves. So this is also important because, again, at the end of the day, the role of any of these antennas is to, in the transmitting mode, is to take the power that you're putting into this and then radiate it into free space. Any part of that that's lost in your matching network or due to earth or anything else is power that is not doing what you want it to do. So we need to kind of have these things in mind. Another thing that you need to keep in mind when you are designing impedance matching networks for these small antennas is that when your antenna is highly reactive, so this is a high Q antenna, as is the case for electrically small HF antennas, this matching network, you will have, in your matching network, you will have very large high voltage and high current values. So let's say, you're trying to transmit 100 watts of power through this antenna, and, this impedance matching network is used to impedance match this to 50 ohms. You can have very high voltage and high current values in your impedance matching network to radiate 100 watts of power. So you got to make sure that the components that you're using are rated for the appropriate amounts of maximum current and maximum voltages that you experience. So for example, you may have a capacitor that all of a sudden experiences 500 volts, and the capacitor is not rated at 500 volts, and it gets damaged. Or even in the implementation of your impedance matching networks, you may have wires that may not be that are used to connect different parts of your matching networks together, and they may not be rated for the amount of current that will pass through them, and they will burn, and that damages your matching network. This actually has happened to us in some experiments. So any questions?
Yeah, I was curious, the Q of the antenna, was that have to do with the near field stored energy relative to the radiation resistance, or
Yes,
what was the definition
absolutely.
of that?
So the Q of the antenna, in this case, we're basically defining the Q of the antenna as the Q of any resonator. So that would be defined as the ratio of stored energy to the dissipated power per unit cycle, right? So yeah, the ratio of stored energy to essentially the dissipated power per unit cycle, or you get something like and we also multiply this by 2 pi to get a conversion factor. But the stored energy in this case would be the total stored energy in a near field region of the antenna. And then the dissipated power for a lossless antenna would be the radiated power. And then when we have an impedance matching network designed for that for that antenna, then there's going to be the antenna would be resonated out, and so we are going to have some energy also stored in our impedance matching network. But the Q of the antenna is defined based on this equation, and the stored energy is the near field stored energy.
All right, thank you.
You're welcome. Any other questions before we proceed?
I have a question regarding that ground plane simulation you did. Is there any effect if the ground is not flat or it's not smooth?
Absolutely, there will be, but in these cases, what we've done is we basically haven't taken we're assuming that locally this is flat, but there will be effects absolutely. If, for example, you have like nearby objects, or your let's say if the ground plane is sloped, all of this will impact your radiation pattern. These calculations, the good thing about considering a flat ground plane is that there's a closed form, sort of a Sommerfeld integration formula that you can use to calculate the radiation from these structures in the presence of real Earth, sort of analytically, right? And some softwares like FICO have actually implemented that, so they make it really convenient, to analyze antennas in the presence of real Earth. I think the old NEC software also had that capability as well. When you make it, let's say if the ground plane is not flat in the vicinity of the antenna, then that analysis becomes much more difficult. I'm not aware of closed form or formulations that are there, so this has to be done numerically, right?
Thank you.
You're welcome. So let's see. So yeah, so again, the voltage rating and current rating of your components also quite important. So here I'm also I'm sort of emphasizing on this matching network quite a bit, because this is extremely important. This is like in these small antennas, especially at HF. The types of antennas that we end up using in many cases in our dipoles and loops and things like that, these are relatively simple antennas. And a lot of our power is actually lost in the impedance matching network. And designing better matching networks and higher quality matching networks buys you a lot of buys a lot for the amount of investment that you're making. So here, what I'm showing here is what happens in this impedance matching network for this monopole antenna with a top hat that has 4 radial wires that we examine. What happens to the loss of my impedance matching network when the quality factor of my elements, my inductors and capacitors, are changed? So I start from really high quality elements, inductors with a quality factor of 100 and capacitors with a quality factor of 1,000, and then go to some more practical numbers like inductors with a quality factor of 10 and capacitors with a quality factor of 100, and notice how much my impedance matching network losses go up, from 4 dB to about 12 dB or so. So we have approximately like 8 dB of gain change in our antenna as a function of the impedance matching network. And so you can have an antenna that has, let's say, 8 dB lower gain because of the components that you're using in your impedance matching network. And of these components, turns out that your inductors are actually really important, because we tend to use pretty large inductors at these HF frequencies, and our capacitors are not as large. So for example, in this table, if we keep the quality factor of our inductors fixed at 100 and then reduce the quality factor of our capacitors from 1,000 to 10, then we'll see that our matching network losses go up by about 0.7 of a dB. But then, if I keep my quality factor of the capacitors fixed at 1,000 and then reduce the quality factor of my inductors from 100 to 10, notice that, I go from 4 dB to about 11.8 dB or so. So inductors, we need really high quality inductors. So if you're designing an HF antenna system, and if you want to invest energy in improving the gain of the system, trying to design matching networks that have really, really high quality inductors, would be a good investment of time because, we end up having pretty large inductors in our systems, and the losses, become very important. So, Sima, I have a quick question for you. We are coming up to about 10 minutes or so. Do you want me to stop sharp at 2 hours, or can we go maybe 10 minutes over?
It's up to you if
Okay.
you want to go over. Yeah.
Okay, so we'll see, because I think I probably have like maybe 2 hours and 10 minutes worth of
Okay.
stuff. Okay.
Okay.
All right, very good. So let's also very quickly look at what happens when we have horizontal antennas, right? If I have a horizontal dipole, again, I can use my image theory, and if obviously the image theory applies when we have a perfect electric conductor, but when we have horizontally oriented antennas, the image of the antenna is in opposite direction to the original radiating current, right? So when the separation between the antenna and the ground is pretty low in terms of the wavelength, you can imagine that these are sort of canceling each other, and your antenna becomes less efficient. But there are reasons why we may want to use horizontally polarized antennas as well. So one of these reasons that I mentioned was maybe we want to have NVIS type applications, and in an NVIS type application, you want to launch your wave directly towards the ionosphere. And in that case, if you're dealing with a dipole antenna, using a horizontal dipole antenna makes more sense than a vertical dipole, because the vertical has a null in that direction. So you can go ahead and do a very simple analysis for a horizontally polarized antenna or a horizontal dipole on a perfect electric conductor. And this horizontal dipole, will have an array factor that you can plot and see how it changes. And this is something that we all do in our antenna courses, and it's pretty straightforward. Now, in real Earth, though, our real Earth is not a perfect electric conductor. So you kind of have to, if you want to figure out exactly what happens with your antenna, you have to do that modeling, use, let's say, for example, a software like NEC or FICO to do this analysis. The general trends are still the same, that, you'll have some image currents that would be oppositely directed to your main radiation. But, let's see what happens here. So I've done some simulations here, and I'm showing, the radiation pattern of a dipole antenna, a 3-meter dipole antenna at 10 megahertz, placed horizontally on top of a real Earth with dielectric constant of 20 and conductivity of 3 times 10 to the minus 2. And what we are looking at in this figure here is what happens to the radiation pattern of this antenna as a function of the height of the antenna above this real Earth here. And so this black curve shows a height of about 1/16 of a wavelength. This is approximately 1.9 meters or so above the ground. And you can see that as I increase this, the gain increases, right? Because this 1/16 of a wavelength is not a very large separation between the antenna and the image current that's oppositely directed to that. So you don't get very efficient radiation. But as you're increasing the height, and the ideal height obviously is a quarter wavelength here, then your radiation improves. Now, at 10 megahertz, a quarter wavelength is 7.5 meters. It's approximately 24, 25 feet. So this is not an insignificant number, right? So putting a dipole antenna horizontally 25 feet above the surface of the Earth may not be very practical. And so there are, in more practical situations, especially if you're a person that you're trying to put up an antenna and you don't have access to really high places to hang this antenna from, you actually may be dealing with things like that. Now, these sort of radiation patterns, especially the ones I'm showing here, this blue and red and black curves, these have their maximum radiation towards zenith here, and then so you're basically launching the waves vertically up towards the ionosphere. So these are radiation patterns that are good for NVIS type applications. on this figure here, we are seeing what happens for the antenna. Let's say, this antenna that's now placed at a height of about 1/8 of a wavelength, approximately 3.75 meters above the planet, above the surface of the Earth, as a function of the conductivity of the Earth. And notice that, here, again, we are starting from a poor Earth to, a conductivity of seawater here. And we'll see that again, as the conductivity improves, my radiation, improves, and I'm getting better and better gain values, from this system, for a height of about a quarter wavelength. Now, something interesting happens here because, as I'm changing my ground plane type, so this is a poor Earth, right? And this is almost like, PEC, seawater. So as I'm improving the quality of my ground, notice that, the input impedance, the real part of the input impedance of my antenna goes down, because as the ground becomes a better and better conductor, the cancellation between the main current and the image current becomes better and better, right? So now the real part of my input impedance has gone down. And so my antenna has become more reactive, and the matching network losses have gone up. However, the realized gain of my antenna, despite this, has improved slightly, and this is because of the fact that as I improve the quality of my Earth, I'm losing less and less power in the Earth itself. So, for example, here, which is seawater, which is almost a perfect electric conductor, the waves don't really penetrate there, so I'm not losing a lot of energy in the Earth itself. So this is sort of an interesting case where your impedance matching network becomes harder. Losses go up, but but losses on some other thing due to Earth go down a little bit, and you end up having some sort of a net gain in this case. And so this is also a situation that will be different for different heights of the antenna, the horizontal antenna above the planet. So this is something that if you're ever in a situation that you need to use an antenna like that, you need to be aware of. So there is also another type of antenna that we can use. It's an electrically small loop antenna. This is also used conventionally at HF frequencies as well. And if you have a small loop antenna that are placed on the XY plane, the radiation from this loop antenna would be the dual of the radiation from the Hertzian dipole antenna. So you'll get basically the same donut-shaped radiation pattern. Your polarization would be orthogonal to this, and so it's very similar type of antenna. However, if you actually take this loop antenna, and rather than putting it in the XY plane, let's say, for example, XY plane represents the surface of the Earth, and then the Z-axis is perpendicular to the surface of the Earth. So now I have my loop antenna perpendicular to the Earth. I can take advantage of the shape of the radiation pattern of this antenna, this donut shape of the radiation pattern of the antenna. And if I look at the radiation pattern of the antenna in the azimuth plane, I have that figure 8 shape radiation pattern in the azimuth plane, and I have vertical polarization along the azimuth plane as well. Now, in this case, by the way, the polarization along the positive Z direction or towards the ionosphere would be horizontal. So this antenna on its own would also be good for NVIS type application, but you can also take advantage of its properties of its vertically polarized radiation along the azimuth plane to do some interesting things. What are some of these interesting things that you can do? Well, one of the things that you can do is you can take your Hertzian dipole antenna and this Hertzian loop antenna or magnetic dipole antenna, and you can combine the radiations together, because there is a inherent 90-degree phase shift between the fields that are radiated by Hertzian loop antenna and a Hertzian dipole antenna. And because you have this sort of a omnidirectional radiation from a dipole and a figure 8 shape radiation from a loop, in the azimuth plane, I have an omnidirectional radiation from a dipole, and I have a figure 8 shape radiation from the loop. If I go ahead and combine these with appropriate excitation coefficients and with appropriate weights, I can get a directional radiation pattern. I can get a cardioid shape radiation pattern that looks like this, in the azimuth plane. So I can do this with an electrically small antenna, which is, in this case, for example, in this simulation, an antenna that has a maximum linear dimension of 3 meters that I have shown, and you can get a pretty good front to back ratio. So you're directing your radiation towards one direction and then, suppressing the radiation from a good portion of the back side of this. So this is not going to be a very directional antenna, but, as far as electrically small antennas are concerned, you can actually make it, sort of unidirectional with this cardioid shape radiation pattern. So you can go ahead and implement this, using the same monopole arrangement that I showed, put it on a real, ground plane that's placed on real Earth, and you see that, you get radiation patterns that, that look almost unidirectional, with good front to back ratios, but you also get the same change in takeoff angle that I mentioned, which is a consequence of having real Earth, in your actual system. So you can think about, more realistic implementations of this. Again, if you have a bunch of wires to build your antenna from, and these antennas tend to be physically large, you can implement, your combination of a monopole and loop antenna using a structure like this that I'm showing here. So what we're looking at here is, this is a monopole antenna here with a bunch of radial wires. So these radial wires are basically my ground plane for the monopole. There's some radial wires on top that are the top hat for my monopole. And then there is a loop antenna that, is in this place. And so you take these, you combine the radiation of these two elements with appropriate excitation coefficients between the loop and the monopole, and the whole thing is placed on real Earth here, and you can get a pretty directional radiation from this, sort of a pretty directional radiation in the context of a small antenna from this, with a cardioid shape radiation pattern where you'll have a maximum radiation in one direction and a null in the other direction, and this would be a sort of a one way of getting some sort of a directional radiation from a relatively compact and a small antenna at HF, with a technique that you can reasonably easily implement it with bunch of wires that somebody can put up together. A side sort of note on combining the radiation patterns of loop and dipole antennas is that because their radiation pattern or the radiated fields of an electrically small dipole and an electrically small loop are 90-degree phase shifted with respect to each other in all different directions of a space, in every direction of a space. If you actually combine these two, you can get a perfectly circular polarized antenna as well. So that one, I'm not sure. That one has been sort of a curiosity for me, but it's worth mentioning that this is, also possible. This would basically give you circular polarization in theory in every direction, and not just in specific directions. So that brings me to the almost to the end of this short lecture here. So we talked about some important considerations in designing HF antennas. So there are a lot of things that are important. First of all, kind of need to know what your mode of operation in HF is, because that determines what sort of antenna you'll need to use. Each mode of operation has different radiation pattern requirements. One thing that we saw, which was very important, is you need to reduce the feed point quality of your antenna by any means possible, right? So because that will significantly simplify, the subsequent stages of the design of your RF systems and impedance matching network, to the extent that you have control over your ground. Proper ground plane selection is important, to the extent that you can, use more radial wires or emulate a good ground, that would actually have really important payoff. But in many situations, this is out of our hands, right? In many situations, especially if you have to put up antennas, in the field, you have to work with what you have available. And in those cases, for example, it may come down to using more radial wires in putting up vertically polarized antennas. Whatever you do, if you ignore the properties of the Earth that is in the vicinity of your antenna, you will pay for it. So you have to take that into account. This is extremely important. And then also your impedance matching networks. The losses in this impedance matching networks are important. If you're a designer, if you want to invest your time in improving something, designing good inductors is really the key, and making sure that the power handling analysis has been done, that you're using components that are rated for the power levels that you're dealing with. This is also very important. And finally, if you're dealing with a receive-only application, don't forget that you are likely going to be externally noise limited in many situations. So with that, I'll be happy to answer any questions that you may have, and I appreciate you for your patience with me.
Thank you very much. I was curious, what is the typical expected losses in dB of the ionospheric refraction?
So that would be that's a great question. That would be that depends on sort of your mode of propagation and on your distance, right? So for example, how many hops do you have? Are you passing? So in short, I don't have a perfect answer for that, but I can talk about some of the factors that impact that. So for example, imagine that I am trying to communicate. So this is my transmitter here, this is my receiver here, and there's this D layer, and then there's the E layer, and then there's the F layer, right? So depending on what frequency it is and what takeoff angle I have, let's say that I'm going up and then I'm having my reflection from the F layer. So whenever my waves pass through the D layer, chances are that the critical frequency of the D layer is generally low. So chances are that we are not actually reflecting anything from the D layer, but the D layer is absorptive, so it absorbs my my energy. Similarly, if I'm passing through the E layer, then I'm losing some energy through the E layer as well, and then I have my refraction from the F layer. So this would give me like one mode of operation, and then another mode of operation would be, for example, if I'm working at night when now the D layer is disappeared, and then the E layer is also very weakened, and so the losses are not as high, and I'm reflecting from the F layer. So in that case, my losses would be lower. So all of this is sort of like really time dependent. What time you're working, what path you're working. These are things you can model. There are commercial softwares that you can use to model this, but it will be highly variant, depending on where you are and what time of the day you're working and what path you're working.
You mentioned also a tool called NET, I think, or NEC versus FICO. What was that
Yes.
other one that you mentioned? How do you spell that?
So this the NEC, so I think it's numerical electromagnetic computation or something. So this is a software, a method of moment based software that uh, is particularly suitable for like wire type antennas. So if you Google this, there should be
Yeah, I
out
remember that
there.
now. I
Yeah.
forgot about it and didn't
Yeah.
understand what you were referring to. Yeah,
Sure.
thank you.
FICO, no problem. FICO is a commercial software, and for those of you who are students, you can get free student licenses and work with it. It's a great software. I'm pretty happy with it as well. All right. Any other questions?
There aren't any other. One other question was, I'm kind of new to ham radio, and I've seen some of the antennas that folks like to use for
Yeah.
compact and reconfigurable, and like typically maybe a width of about 80 centimeters or so, and or 65 centimeters with
Sure.
a large coil that's kind of has a adjustable inductor. As you adjust the bar and change the shorting location. Would you expect that you would need to model the antenna with that coil in the presence of the antenna, or is it you just model the antenna separately and then you consider the coil just part of a circuit matching network?
Sure, I think you can do it either way because as you mentioned, the coil is really part of the matching network, right? So what you're doing here is you're basically inductively loading it to make it resonant, right, or bring it
Mhm.
close to resonance. And if the antenna is pretty small, you still need to tune it, with an impedance matching network. But let's say in the ham radio context, if you do that, then depending on the radio you're using, in a lot of these ham radios, they have automatic impedance tuners, in the output stage of their own ham radios, but some
Mhm.
of them also, but you can also use an external, an antenna tuner as well. But the purpose of this would be to just sort of resonate it out because if you just have a monopole antenna, you essentially have like some sort of an RC type network, and then this inductor, you're adding your coil to sort of reduce the feed point reactance of that, or even resonate that out.
Mhm.
But it's still, this input impedance, the real part of that would not be for a small antenna, would not be a 50 ohm antenna, so you kind of need to use a tuner. And I think either one should work well. It's
Mhm.
I don't see any significant difference between the two ways of modeling that.
Mhm. Thank you.
By the way, ham radio is a great hobby. I mean, I love it. It's
Okay, it looks like there's no more questions.
all right.
Thank you. Thank you so much. It was very
My
interesting
pleasure.
talk.
My
Thanks
pleasure.
for offering that to us. And for those who are attending tomorrow's lecture, it's going to be at the same time. If you are interested to see that one, which is the meshless method for solving electromagnetic problems, and you didn't get the invitation, please email me. I can send you the Zoom link. Thanks, Professor
Thank
Behdad.
you. Thank you very much,
Thank
Seema.
you.
Thank you very much,
Yeah,
everybody.
and have a
Have
good,
a good weekend, everybody.
Thank
you
you.
too.
Thanks. Yeah.
Thank you.
Bye-bye.
Bye.